Hello friends, this is the new video on capacity design. In this video we shall be learning what is meant by capacity design, how to implement it, what are the implications if it is not implemented, and so on. So definition goes like this: the capacity design indicates a willful and purposeful way of design where the designer forces the structure to fail in some desired mode and avoids failure in some undesired mode. So when structure fails, all the failure modes may not be desirable. Those modes which gives us early warning of failure, those modes which can undergo large deformation without failure, and those modes which can give us energy dissipation through ductile failure are the desired modes of failures. The chain analogy is very popular in discussing with the capacity design concept. In the chain you have several links, and suppose the links are under tension. Now some links may be brittle, some links may be ductile, and in what way they should fail so that my system will fail in ductile way. So in this slide we have chain with one ductile link here shown by red color, and which is shown by another chain here with golden colors. Gold is very ductile and malleable, so we have taken golden link. So obviously this golden link will be a ductile link, and rest of the links, whether steel or brass or whether cast iron, will be brittle links. Now let us see what is ductile failure and brittle failure. In the force deformation behavior, in the beginning the system behaves in a linear way, so you get a straight line response. Gradually you attain some non-linearity and the curve falls gradually, becomes non-straight line, that becomes non-linear, and at certain point it snaps out or breaks, so that is the ultimate displacement it is undergoing, and the point where it has yielded is the yield displacement. And we have seen our previous video that the ductility displacement ductility mu delta is given by delta u by delta y. In our video number EQ6 we have discussed ductility. So at the red color indicates a ductile system, and in the contrast the violet color is indicating a brittle failure system. So what happens to the brittle failure system? It fails not only at lower force, it fails also at small displacement here. So it is unable to suffer large displacement and it breaks before that. So that is not a good thing during earthquake, when your system will be swinging to large displacements. So this contrast is clear, and we want a system which is ductile, so that it undergoes large displacement, it has more ductility, and it also is able to dissipate the absorbed energy. So energy dissipation process is shown here. This is what is called hysteresis. Let us first consider the red response line. So in the beginning force response diagram is straight line, then it is yielding, then it is going like this and reaches a final point. If the load is now reversed, then it will follow this path which is going downward, that is the compressive force is reducing. Then the force reverses in direction, because this is below the horizontal axis, load is under tension here. At certain point again there will be reversal of the load in the earthquake, and it will again start attaining load, and at this point tension load will be no more, again compressive load will start. So it goes and makes a loop here, and the loops may continue as the system vibrates. Loops after loops will come, and it will continue like this. Now each loop dissipates some amount of energy which is given by the area of this loop. So for the red colored hysteresis loop shown by a ductile system, the yellow hatching area is the area which will be giving you the energy dissipated per cycle of hysteresis. Now in contrast, let us take the brittle system, which is shown by the violet color. So it has reached to this point, after which it is reverses due to the reversal of the earthquake load and comes down, and at certain point again it picks up the load and gradually goes to this and makes one cycle. Since the largest displacement suffered by the brittle system was limited, so the area of the loop is also much smaller. So brittle system will be dissipating energy, which is shown by the violet hatching in this diagram. So this hatch diagram area is much smaller than the red, yellow hatched hysteresis shown by the red lines. So brittle system will be dissipating very less energy in contrast to the ductile system, and it is not desirable because during earthquake our structure will be absorbing energy from the earthquake through its elastic condition, and this energy has to be dissipated out so that the structure is safe. Now what are the advantages of ductile failure that we want? Advantage of ductile failure avoids breakage even at large displacement. So during earthquake there will be certainly displacements, and depending on the force exerted from the earthquake, there may be large or small displacement. So if your system can survive the large displacement, it will survive collapse. Ductile failure is gradual and time taking. So it takes place slowly, so occupants get sufficient time to evacuate from the structure during the earthquake. Ductile failure gives enough warning before failure. How the warning comes? Warning comes in the form of cracks. So visible cracks will be developing in elements like beams, columns, etc. And initially the cracks will be small in size, and that will give warning to the occupant that something is going to happen in the next few seconds. Ductile failure can dissipate large amount of energy through hysteresis that we have just seen. Ductile failure generally avoids collapse of structure. So collapse of structure can be avoided if your system is failing in a ductile manner. Now in the contrast to it, in the brittle system, it has many disadvantages. What are those? Brittle failure invites breakage even at small displacement, which is undesirable. Brittle failure is sudden. So occupants do not get sufficient time for evacuation during strong earthquakes. Brittle failure does not give enough warning before failure. That is, those cracks formation will not be visible. Suddenly it will fail. Brittle failure can dissipate only a limited amount of energy through hysteresis that we have seen in the previous slide. Brittle failure leads to easy collapse of structure. Now let us see exactly the flexural and shear failure of beams. A flexural failure is gradual, is ductile failure. So if it is a flexural failure, you have some load, either UDL or point central load. The flexural cracks will be developing at the point of maximum bending moment, which is at the middle of the beam at this condition for simply supported beam. The cracks are more or less vertical, and this is around the point of maximum bending moment. Our bending moment diagram is here, which has a peak at the center. So in flexural failure, what happens? Even when the structure is sagged down because of failure, it is not snapping out. It is still hanging with the rods inside, and it is able to carry most of the vertical gravity loads. So it will not lead to the collapse of the structure in flexural failure. In contrast, let us see the shear failure. Shear failure takes place at the point of maximum shear, which is at the end of the beam. For this case, a simply supported beam, the maximum shear is at the left end and right end, and the shear cracks are also developing at the two ends of the beam. Shear cracks will be generally diagonal in nature, inclined. So it is inclined, you can see here, shown theoretically, and in practical failure also it is shown as diagonal here. So these cracks will take place suddenly and it may lead to failure of the system also. So this shear failure is to be avoided and flexural failure is desirable. It is a means comparative word. We want flexural failure doesn't mean that we always intentionally want a failure. No. When failure is inevitable, then we want that our flexural members should fail and not the shear members or the compression members. So what are the elements which can show ductile failure? There is a question. The beam under flexure will be failing in ductile manner as we have experienced. Shear wall under flexure will be failing in ductile manner. So let us see, a beam is considered here which is a propped cantilever. This side is fixed, then this side is over a hinge having a central root, so it will sag downward. In the beginning it will sag in an elastic way without any fracture, but gradually as the load increases it will fail by flexural failure at the center. So maximum bending moment will be at the center, so it is failing at the center. And you can note here, even after failure the rods have not snapped out and the beam is still hanging, so it is able to take the vertical load. During earthquake, if you are sitting here over the beam, you will not fall down because the beam is not snapped out. In a shear wall where the vertical rods are there, horizontal rods are there, the yielding takes place in the maximum bending moment zone, which is at the bottom and on the convex side of the wall, which is shown here. Now shear wall is a deep beam we have discussed in previous slide. So its depth is here to here, which is the length of the wall. As the beam is deep, it undergoes large flexural hinge formation and it can dissipate large amount of energy while it is failing or when it is showing nonlinearity. Failure in columns is under compression or also maybe under shear or a combination of shear and compression. A compression failure is shown here where a part of the column is failing and this failure is also sudden. It is brittle in nature. All column failures are brittle in nature. It can fail by diagonal shear forming diagonal cracks here. As seen, this is a shear failure of the column. It can fail in buckling. Buckling, you understand, the column bends like this. So initially it will bend elastically and then as the displacement undergoes more and more magnitude, it will form cracks on the convex side and it will fail like this. It can also fail by forming bulging. So what is that and how it occurs? You have the ties or the horizontal stirrups given in the column. If these stirrups are not sufficient, if their spacing is too large, if their diameter is small, or if there's amount required to be provided that was not provided, then what happens? The ties will snap out. As they snap out, they are unable to hold the vertical steel in position. So vertical steel now goes outward, bends and forms a bulged condition in the column and it is a column failure. This is also brittle failure. Now let us again go back to the chain analogy. We have suppose the cast iron links shown by the grey colors and we have taken one golden link shown by the golden color. Obviously the cast iron is brittle in nature, it will not undergo much displacement and it will fail. Whereas the gold is very malleable and ductile, so it will undergo large displacement. So this link is acting as the ductile link in my chain. So chain is under actually pull, so these are the two forces shown. The ductile link is undergoing displacement without failure, it is undergoing ductility. So there is the way of showing ductile link in the system. Now question is how many ductile links you shall put, because the gold is costly. So how many ductile links, that is the question, natural question. In this case, the B is showing the brittle links and D is showing the ductile links. So our golden link is ductile in nature. We have put only one ductile link in the system. There can be alternative ductile links as shown in the second figure. So which one is desirable out of that? Or you can have all the links ductile. So obviously in the last case, third case, all the gold links, if they are all costly. And even when it is RCC, to make the system ductile, you need additional reinforcement to be provided, which makes it costly. So the third option will be very costly, second option is also costlier. First option is least costly, but whether it is viable. Now when one link is undergoing displacement, undergoing the extension, then your whole chain is extending and it is able to absorb the displacement demand arising out of the earthquake. If you put more links, then more displacement will be there and this system may not be useful at all. If your chain is extending to half a meter, then it is not a chain anymore. So a single ductile link should be able to absorb the displacement demand of the system, and one link should be sufficient in a chain. Now relative strength of the links, because we have the ductile link and the brittle link. So what should be the strength of the ductile link and what should be the strength of the brittle link, so that my failure is ductile in nature. So obviously if the ductile link has to fail, undergo inelasticity, then its strength should be lower. If we put SD as the strength of the ductile link and SB as the strength of the brittle link, then the relationship is very simple. SD is less than SB, so that ductile link will be failing. But how much less? Is it twice less? It is 3 times less? So that question arises. So we can in a simple way say the extreme strength of the ductile link is less than the limit strength of the brittle link. The strength level we have seen in our previous video. So we understand what is extreme strength and we understand what is limit strength. So limit strength is the least strength exhibited by the system and extreme strength is the highest possible strength exhibited by the system. So if the highest strength exhibited by the ductile link is less than the smallest strength exhibited by the brittle link, obviously in all cases the ductile link will be failing, because the characteristic strength, SB characteristic or SB extreme, etc. will be, or SB mean will be always higher than SD extreme by this condition. So if we follow SD extreme less than SB limit, then it will always ensure that your ductile link is failing and not the brittle link, and as a result your system is failing in ductile manner. Now beams and columns meet at a joint and they can be considered something like a link, a chain. So beams are there and columns are there, and which should fail? That is a question. We have seen the beam fails in flexure and column fails in brittle condition. So beam failure is desirable in the link. Beam failure is desirable, and this goes by the name weak beam, strong column condition. Column failure is brittle, beam failure is ductile. Column should not fail, beam may fail in extreme condition. Column strength should be more than beam strength, so that column is not failing. So columns are generally more than one at the upper story and then lower story. So we can write it like this: the sum of the column strength at a joint in one direction divided by the sum of the beam strength at that joint in that direction should be greater than 1. That is, the column strength is higher than the beam strength, and then columns will not fail. So this condition we have just seen, let us now write it in mathematical format. The summation of MC limiting divided by summation of MB limiting should be greater than 1.0, so that the columns are not failing. MC is the limiting, MC limit is the moment moment of resistance of the column in limiting condition. And MB limit is the limiting moment of resistance of the beams. So these are the minimum strength shown by the limit strength level for the columns and minimum strength shown by the beams in the limiting condition. Their ratio should be more than 1 so that the columns are stronger. Now if just how much stronger is not defined, so the code has defined it like this. How much stronger? So IS 13920 2016 says this MC limiting summation divided by MB limiting summation should be more than 1.4. So code is supposing that if this is more than 1.4, always the beam will fail and not the column in the joint series. In the Eurocode 8 2003, the value is 1.3, a little lower. So these are the limits given by the anticipation of the course. Now in the research, my finding is this, that in high-rise structures, high-rise buildings, this value should be much more higher to arrest the failure of the columns. You may require value of 2, 2.5, 3, etc. so that column is not failing. This happens because of the amplification in high-rise structures, amplification of the action effects towards height. So there you may require more than these defined values of limits of the ratios given in the code. So we have to remember that this limit, this summation of the column moment and summation of the beam moment is in a particular direction. So in a building we have two directions, x and y. So in both the direction individually these limits are to be satisfied. We have shown a joint here, beam column joint, where 4 beams and 2 columns are meeting. One beam is from the left, one beam is from the right. One beam is from our forward direction, another beam is from our backward direction. So these 4 beams and 1 column at the top, 1 column at the bottom, 2 columns. So they all are meeting at this joint, beam column joint. And when you apply this condition given by the code, you have to consider direction by direction. For this direction beams and the strength of the column in that direction bending. So this ratio that we have discussed, the summation of column moment to the summation of the beam moment in the limiting condition, is also known as column to beam capacity ratio given by C by B ratio. So I have analyzed a 4-story building, RC building, and found out in SEP 2000 what are the C by B ratios for different columns. So the ratios came out like this. You can see in every column you are getting 2 values. These are in the 2 directions, x and y directions, and the values have come here much higher than the limits, 4.044, even up to 4 point something. So these are higher values. This has arisen out of the condition that the building was not optimized. The design was not rechecked again and again to optimize it. That's why the values are higher. Higher values indicate columns are much higher than the beam and there may be some wastage of material in the column. What happens if the columns are weaker? Columns will fail first. When column fails, there are a lot of problems. Suppose there are 10 columns in a floor in a building and 1 column fails. So this column is unable to carry the vertical load. So this load has to be carried by other columns now. So adjacent columns take the load of that failed column and the adjacent columns now become overloaded. Now earthquake is taking place and the column is overloaded over its design load. So these columns also will fail gradually. When the second column fails, it imparts much higher load to the adjacent columns after the failure of the second column. So gradually the third column will fail and so on. This is what is called the progressive failure of columns. So this progressive failure will be sudden and without prior warning in columns that we have seen. columns failure shall lead to instability. What is instability? Your structure may become unstable and it may collapse. This is one thing. Another thing is the instability in the analysis. You can see here the beams have failed. The color dots are showing the hinge formation in the members. For example, if we take this joint, the right hand beam has failed, left hand beam has failed or has become non-linear, as well as the top column has failed and the bottom column has failed as shown by the hinge. So if all the members meeting at the joint fail simultaneously, they form an unstable condition here and analysis will not progress further. That is, whatever analysis procedure you apply, it will not be able to close to a solution. So your analysis in the nonlinear analysis, it will stop simply. You are not able to run your earthquake analysis for the full time of the earthquake. So this you can say instability in the analysis. If we make a gist of what we have learned in this video of capacity design is forcing the structure failing in some intended way. The intended ways are, as we have seen, it should fail in ductile way, it should fail in flexural mode instead of shear mode, torsional mode, buckling mode, etc. Flexural failure is desirable over compression failure, shear failure, torsional failure, etc. for the reasons we have already discussed. The extreme strength of ductile link shall be less than the limit strength of the brittle link so that the failure of the ductile link is ensured. Building should be designed as per strong column weak beam concept so that the columns are not failing and beams are failing and able to dissipate energy during earthquake. Failure of columns may lead to instability, as we have discussed. Instability in the physical building and instability in the model in the computer when you are making nonlinear analysis. Let us take an example, numerical example, to understand what we have learned in the capacity design. For that purpose, we have taken a beam column joint with 4 beams meeting at the joint. It is shown in plan. So column you are seeing as a cross section, the white one at the center, and the 4 beams are meeting at the joint in the plan. The x directional beams are shown by green colors, size is 350 by 500 millimeter, and y directional beams are shown by grayish color, whose size is 300 by 450 millimeter, and the top steel, bottom steel are given. Column size is 400 by 450 millimeter with 8 number of revers of 20 mm diameter. Our question is like this: 4 beams and 2 columns meet in a joint. The clear cover is given, and the grade of concrete is M30, grade of steel is Fe500. The axial force in the top column is 300 kilonewton, and that in the bottom column is 400 kilonewton. The diameter of shear is 8 millimeter. Find the C by B ratio, column to beam capacity ratio. There are 2 columns, one column at the top floor and one column at the bottom floor, which is not visible in the plan. So the plan is shown again here, and let us start calculating for the x directional beam. The size is this here, so we can calculate the amount of steel at the top and bottom, effective depth, and the effective depth for the compression steel. Strain in tension steel is given by epsilon s equal to epsilon c d minus x by x, and similarly strain in the compression steel is given by this. So we prepare a table like this, where we select some value of the neutral axis depth x. This we have discussed previously in another slide. Then this is the strain in the tension steel. From this strain we shall get the stress in the tension steel. From this stress multiplying by the area of the tension steel, we get the total tensile force in the tension steel. And we calculate compression in the compression steel. From that we find the stress in the compression steel, and from that the compressive force in the compression steel. And the compressive force in the concrete is given by standard expression 0.36 FCK-BX for Indian code. Find the total compression CS plus CC. and now check whether C is almost equal to T or not. If not, then change your value x. So we started arbitrarily with the initial value of x as 150 millimeter. So we see that T is here 409.8 kilonewton and C is 809.1 kilonewton. Indicates C is much higher than T. So we have to reduce the neutral axis depth. So we have taken it 100 millimeter. Here also again C is much higher, so we have reduced to 90, then 70, then at 67 we found that 409.8 and 410.7 C and T are almost balanced. So we consider 67 millimeter as the neutral axis depth for this section where equilibrium has been reached in compression and tension. So now we can find out the moment of resistance of this section by this formula as shown here, available in the books, and we got the moment of resistance as 173.8 kilonewton meter. So this is the limiting moment of resistance for the x directional beams. X directional column you can take, column at the top floor and column also at the bottom floor. So there will be two capacities of the columns for each column, x directional, y directional. So there will be 4 capacity of the columns in total because 2 columns and 2 directions. We take the help of SP16 of Indian publication. We find out the amount of steel percentage and find this ratio P by FCK. FCK was 30 megapascal is this, and find out this PU by FCK BD, which is 0.083 by calculation. From chart 50 by SP16, MU by FCK BD square is this 0.075, and so MU is this. So the limiting moment of resistance of the column at the top floor is 182.2 kilonewton meter. At the top floor, you remember the force was 300 kilonewton, and you have to multiply it by 1.5 partial safety factor to get the ultimate axial capacity, which is 450 kilonewton here. In the same way, you can find out moment of resistance in the YY direction, which is found out as 98.4 kilonewton meter. So you prepare a table now, direction x and y, beam moment from left from right, and total summation here. Similarly, column from top, from bottom, in x direction, in y direction, and the summation. So C by B ratio in the x direction is the 376.6 column capacity summation divided by beam capacity summation 347.6, which is 1.08. In y direction, the column capacity is 410 and beam capacity summation is 196.8. You take the ratio, you get 2.08. Now if you make a comment on the CB ratio, 2.08 is more than 1.3 or 1.4 as given by the codes. So this y directional strength is alright. In the x direction, it is less than that, those values 1.3. So this is not safe. CB ratio is not satisfying the codal condition. So how to overcome this? You have to increase the capacity of the column. If you increase the capacity of the column, this numerator will increase and this value also, ratio will also increase. How to increase the capacity of the column? First you have to try by increasing the amount of steel. So suppose your design steel was 2.5%, so you can make it say 3%. That will enhance the amount of steel and increase the capacity. But you cannot go on increasing the amount of steel because there will be overcrowding of steel. So generally 3 to 4% steel in column is considered to be alright. So with this percentage steel, if you are unable to get the CB ratio required, then you think of increasing the size of the column, and then C by B ratio will be satisfying. Thank you very much. Please subscribe the channel, watch the videos, share the videos, and you can put your inquiries in the comment box. I shall be glad to answer those. See you again in the next video. Thank you.